Circle gamma has center O and radius 9. Circle omega A has radius 2 and it's internally tangent to gamma at point A. Circle omega B has radius 3 and is internally tangent to gamma at point B. The common external tangents of omega A and omega B meet at point T. Given that TO is equal to 2 times AB, compute AB. So we're given this diagram here, and obviously we have these tangency points, so obviously we should draw in these lines, in which case this length here is 7, and this length here is 6. Right. Now what else do we notice? Well, we want to somehow relate this point T with the rest of the diagram. And looking a bit at the diagram, we end up suspecting that T, A, and B are collinear. So how do we prove such a thing? Well, actually, this is a generalization, actually a specific case of a more general theorem, called Mangi's theorem. So suppose you have 3 circles here, then you construct the common external tangents, the pairwise ones of each, and then finally these ones here. And then they're supposed to intersect over here. Then Mangi's theorem states that all these 3 intersections, I'll label them here, they're collinear, they all lie on the same line. So how can we use this to our advantage? Well, inside our above diagram here, we have that if we somehow set this circle offset a bit such that they are not internally tangent, then if we have something like this, then the external tangents come here. If we have something like this, the external tangents come here. And if we have something like that, then the external tangents be there. The point is that when we get it to be extremely close to the circle, the intersection of the external tangents is basically A. And similarly for point B, and we have point T here. Thus by Monge's theorem, T, A, and B are collinear. So now let's use this to our advantage. Well, since we know that T lies on the line connecting the centers, and also lies on line AB, we actually not need the external tangents at all. I've now gotten rid of the external tangents because we now no longer need them. So now we have our line O1, O2, and our point T outside. So how can we relate T to the line AB? Well, we have these collinear points O1, O2, and T, and we have 2, 7, 6, 3. So there's a natural way to relate AT over TB, and that is the theorem of Menelaus. So by Menelaus' theorem, we end up getting that A01 over O10 times O02 over O2b times BT over TA is equal to 1. Then plugging in the given side lengths gives 2/7 times 6/3 times BT over TA is equal to 1. This just becomes 2. So that means that this is just 4/7. And therefore, BT over TA is equal to 7 over 4. So that means that we can let BT is equal to 7x for some real number x, positive real number x, and TA is equal to 4x. In which case we have that this is 4x and BA is equal to 3x. So finding x will actually suffice. And on top of that, by the given condition in the problem, we know that TA is equal to twice AB, which is 6x. So, and now because we have OA equals OB, the natural thing to do now is to drop the foot of the altitude from O to AB, which is just the midpoint of the segment. So let's let this point be M, then this is a right angle, and that's 1.5x and 1.5x. Now we can use the Pythagorean theorem on triangle TMO and get that 5.5x squared plus OM squared is equal to 6x squared. And then we end up getting that OM squared is equal to 23x squared over 4. And so OM is equal to root 23 over 2 times x. So we can go ahead and add that to our diagram. All right. Now we have length AO as well. That's equal to 9, so we can again use that. So we can now use Pythagorean theorem on this triangle to get AM squared plus MO squared is equal to 1.5 squared is 9/4 x squared plus 23 over 4th x squared. And now the smoke clears with these nasty fractions. This becomes 8x squared, and this is equal to 9 squared. And therefore, x is equal to 9 root 2, 9 divided by 2 root 2, and this is equal to 9 divided by root 2 over 4. And finally, we have that AB is equal to 3x, which is 3 times 9 root 2 over 4, which gives our final answer 27 root 2 over 4. And that's the length of segment AB, as is required by this ARML problem 10 in the individual round. So thank you so much for watching this video. Please subscribe if you'd like to see more.